Welcome to the video on carboxylic acid derivatives. Remember, we talked about carboxylic acids being reduced to form alcohols, and that is a change in oxidation state. However, we can take carboxylic acids and turn them into a number of different carboxylic acid derivatives where we maintain the oxidation state. In other words, that carbonyl remains. So if we look at the different carboxylic acid derivatives, the most common of these are the acid halide, the acid anhydride, the ester, and the amide. Another example that is similar in reactivity to these four compounds is the nitrile. So what we have is a compound that has 3 bonds to electronegative atoms. So in terms of carboxylic acid derivatives, acid halides and acid anhydrides are very unstable and very reactive. They are not commonly found in natural compounds because of their reactivity. Esters and amides are abundant in nature. They are much more stable. Esters are found in nature in the smell of pineapple, banana, and pear. Esters are very often that sweet, fruity smelling compound. And I believe there's a laboratory experiment in the second semester of organic chemistry that delves into these fruity smelling esters. Proteins are comprised of repeating amide linkages. So we call it a peptide bond in a protein. And in organic chemistry, we call it an amide bond. It is the same bond. And that is shown down here. This N bonded to the carbonyl. That is an amide shown in green, and it is also a peptide bond. Amides are found other places in nature, for example, in melatonin. Now, if we look at the reactivity of the carboxylic acid derivatives, the most reactive is the acid chloride, then the anhydride, and those are very similar in reactivity, followed by the ester and then the amide. And if we think about the reactivity of a carboxylic acid derivative, we will just give that an X, meaning something electronegative. What happens is the electrophilic site here is the carbon with this dipole set up with the partial positive at the carbon and the partial negative at the oxygen. And so this right here is an electrophilic site that is going to be reacted upon by nucleophiles. In terms of the reactivity, we have to think about a couple different things. One is induction, right? So the chlorine is an electron withdrawing group that is going to pull electron density away from that carbon, making it even more electrophilic. Same goes for this compound right here. We have that electronegative oxygen. And so induction is going to play a key role in the reactivity of our carboxylic acid derivatives. We have an inductive effect with oxygen as well. And so we have this inductive effect where we have an electron withdrawing group that is going to make this carbon, in all cases, more electrophilic. And so if our compound has resonance, it's going to change the reactivity of the species. Nitrogen is very good in terms of resonance. And so that's what makes this amide much more stable because it actually has resonance structures that are major contributors. Sterics, if our R groups here are big and bulky like a tert-butyl group, that is going to block the site from a nucleophile attack on that electrophilic carbon. And lastly, we got to talk about the quality of the leaving group. We're going to do a substitution where a nucleophile attacks the carbonyl and kicks up to make that tetrahedral intermediate. And then in the second step, that's going to kick down and kick out our leaving group. Depending on the ability of the group to leave, we can have higher reactivity. Chlorine and a carboxylic acid are great leaving groups. So these are going to be wonderful leaving groups, and that is going to make these two more reactive. The OR is a little less likely to leave, but we can trick it to leave, just like we did the OH. And the NH2, same thing. We're going to need to trick it to leave, and so we'll learn how to do that. So the reactivity order goes acid chloride, anhydride, ester, and amide. This is the least reactive, the most stable. This is the most reactive or the least stable. And that is because of a combination of inductive effect, resonance, sterics, and the quality of the leaving group. Here is another table describing the same exact thing. And this is just showing. So if we start with the acid chloride, we can easily convert that into an anhydride because it's lower in energy. We can easily convert that into an ester because it's lower in energy. and we can easily convert that into the amide. And so we will learn all those reactions. If, however, we're starting with the acid anhydride, we can easily convert it to the ester and to the amide, but in order to get it back up to the acid chloride, we're going to have to play some tricks on that molecule. We're going to have to put some energy in, and we're going to have to use more aggressive reagents. Esters very easily go into amides. And again, if we're going to go back up the hill to the less stable species, we're going to have to play some tricks. What I wanted you to notice in terms of this figure that differs from the previous figure is that the carboxylic acid sits here as the central compound, and we can go from the acid chloride to the carboxylic acid, from the anhydride to the carboxylic acid, from the ester to the carboxylic acid, and from the amide to the carboxylic acid. Notice, however, that the carboxylic acid is a little less stable than the amide, so we have to add heat to that reaction. And so this is kind of the central compound, and that's why this chapter is called Carboxylic Acids and Derivatives. I'll briefly go through the next couple slides, but I've already talked about it. In terms of induction, that electron withdrawing group is going to absolutely make this carbon more electrophilic. The more inductively withdrawing group that we have connected to our carbonyl, the more reactive it will be as an electrophile. There's also resonance. Here's our acyl chloride here. We can kick electrons up to form this species right here, and then one of the lone pairs from the chlorine can hop on to form a double bond here. This is not a significant contributor because that chlorine doesn't really like to have two bonds. But the fact is we have resonance in that compound. And in this situation, acyl chlorides are the most reactive, and that is because we have a very good electron withdrawing group and we have little resonance. If we talk about amides, which are at the other end of the spectrum and they are the least reactive, we do not have any induction per se because carbon and nitrogen are very close in electronegativity compared to that of chlorine and oxygen. So we don't have to really worry about any induction. So we're not activating that carbon as an electrophile. However, we do have this additional resonance structure where we have the double bonded nitrogen, which is a significant contributor. You might even remember this question from the previous exam when we talked about the bond length of amides. And so that bond right there is not a single bond. It is about 1.5. A significant amount of time, that is a double bond. And so we end up with this being a major contributor. And so that is going to decrease the electrophilicity of that carbon right there. Being able to rank the reactivities of the different carboxylic acid derivatives is going to be important moving forward. Good luck.